Hi, I am Kim J. I am a PhD student from University of Cambridge. This is a joint work with Deepesh Toshniwal from TU Delft and my PhD supervisor Fehmi Cirak. Our recent work introduces a simple and unified way to define optimally convergent smooth basis functions on unstructured meshes. There is a preprint on arXiv which gives all the details. Here, I will keep things simple and focus only on the key ideas. One of the key advantages of spline basis functions, which really brings success to isogeometric analysis, is smoothness. So in this context, what motivates our work is that how can we construct smooth splines on hex meshes? For example, here is a hex mesh of a sphere. We can see that the extraordinary edges and vertices, as highlighted in red here, are all interconnected. So it is really challenging to define smooth splines in this mesh. Yet, we all know that smooth basis functions are important for discretizing higher order partial differential equations, for example, thin shells and phase field models. Here are the key ideas of our work. We use the partition of unity method to blend two sets of basis functions. The first set is the unstructured splines B, and the second set, the Bernstein basis Q in the physical space. A key novelty of our work is that the wave functions required by the partition of unity method are assembled from standard B-splines. And the procedure is really simple. Let me walk you through that now. Assuming that we are given a B-spline parameterization X, which is injective, so that the inverse is defined, we can first express the B-splines in the parameter space in physical space using composition. And then we define two sets of wave functions. The first we call it WB, and the second we call it WQ. And these two wave functions are assembled from just standard B-splines. So after that, we blend using these wave functions. We blend the B-splines basis with the Bernstein basis in the physical space. And the result is what we call the smooth blended B-splines, or short form SB-splines. As a simple example, here is a line domain parameterized by quadratic B-splines. The parameterization is chosen to be C0 continuous at the midspan, so that we can think this midpoint as the extraordinary point on an unstructured mesh for analogy. So in order to create some smooth basis functions in this line domain, we first define the wave function WB, which is highlighted in red here, by simply subtracting from 1 the splines in the blue color, because they are non-smooth at the midspan. And if we multiply this smooth WB with the existing B-splines, we obtain a set of smooth splines, as you can see here. So you can see that the non-smoothness has been removed. However, as you may have noticed, the splines here, they don't sum to 1, especially in this gray region here. That means we lose the partition of unity property. And as a solution, we introduce the Bézier basis functions in the physical space, in this case, quadratic Bézier basis functions. And we can simply use WQ, which is just 1 minus the previous wave function, WB. And we can blend them, and then to obtain another set of smooth splines, as you can see here. So we arrange all these blended splines into a vector which we call N, and this is the smooth blended B-splines. And we use these new basis functions for analysis. So what is unique about this kind of blending? First, the blending is performed in the physical space. Second, you can see that the blending actually only affects the blending region highlighted in gray color here. So what this means is that outside the gray box here, the SB-splines actually reduce to B-splines. So this is one of the reasons we call them SB-splines. And finally, of course, all these smooth blended B-splines they sum to 1 because of the partition of unity method. So as you can see, it is quite simple. Here is another example using cubic B-splines and cubic Bézier bases. Again, here the resulting SB-splines, they are smooth across the kink. So hence, this blending idea carries over to higher polynomial degrees. Now we are ready to move on to unstructured meshes. We consider unstructured quad meshes on a plane and focus on quadratic case. But really, the idea carries over to higher polynomial degrees. So we first define a set of mixed smoothness splines using Bézier representation. So this construction involves where tensor product is applicable, we have biquadratic B-splines. And where tensor product is not applicable, we have an unstructured spline like this. So using this parametrization across all the edges shared by an extraordinary vertex here, we have some non-smoothness. We have only C0 continuity. Our objective now is to create smooth basis functions in this non-smooth domain. Again, the idea is the same. We first define the wave function WB by removing those non-smooth B-splines. For example, each red dot here represents one quadratic spline basis function that we have seen earlier. Those marked by crosses, they are non-smooth or they are only C0 continuous near the extraordinary vertex. If we remove these basis functions denoted by the crosses, we get a smooth wave function that looks like this. We can see that this is analogous to the wave function in 1D that we have seen earlier. Once we have defined the wave function WB, we can then multiply that with the existing B-splines to eliminate the non-smoothness. So similarly, this is analogous to what we have seen earlier in the 1D example. Similarly, we define biquadratic Bézier bases in the physical space. Here, the top figure shows the multiplication of one of the Bézier basis functions with the wave function WQ. And the bottom figure shows the 1D analogy that we saw earlier. Next, we apply the same idea onto hex meshes. But before that, since hex meshes can have challenging topologies, how can we easily define the wave functions? So to answer this question, we propose this technique known as sector-wise implementation. The idea is that we can choose a sector and we can define some univariate wave functions as highlighted in the red color here in the parameter space. Then we multiply these univariate wave functions, apply the geometric mapping, and repeat for all the remaining sectors. We end up with the same wave function WQ that we have seen earlier. So this technique is really useful to help us think how to define wave functions on a hex mesh. Here is an example where extraordinary edges are connected in a line configuration. We call this configuration a prism. To define wave functions on this prism, we choose a sector and define some univariate wave functions in the parameter space. After that, we apply multiplications and geometric mappings to obtain the wave functions in the physical space that are shown here. So here the red color denotes a value of 1, whereas blue color denotes a value of 0. Here you can see that instead of having just one WQ, there are several WQs over here. And the reason of having several WQs is to ensure compact support of the SB-splines. If we add or sum all these WQs and subtract from 1, then we will obtain WB, which is analogous to the WB that we have seen earlier. Here is another example where extraordinary edges meet at a joint configuration. To define the weight functions on this joint, we again use the same technique, which is splitting up the joint into sectors. So you can see the construction here and the weight functions of the joint and of the connecting prisms. Together with the weight function WB, they all sum to 1. Here comes the final part of my presentation. In order to assess the convergence behaviors of the SB-splines, we have conducted several studies. Here I will just take one example from our preprint, which is the biharmonic problem in 2 dimensions. Here we have a square domain with 8 extraordinary vertices as shown here. We discretize the weak form of the biharmonic problem using the SB-splines, and as usual using a manufactured solution for the convergence study. We have also used a non-necessary refinement scheme for H refinement. Here we have 3 tasks. First, we numerically examine the convergence rates and compare with a priori error estimates. Second, we want to know if the SB-splines require expansive quadrature, so we want to study the effect of quadrature. And third, we want to know if there are any undesirable artifacts if we have high valence of the extraordinary vertices. Using the SB-splines, we observe optimal convergence rates for the biharmonic problem, and that is a convergence rate of order 2 with respect to L2 norm and H1 norm, and order 1 with respect to H2 norm. In addition, using just standard Gauss quadrature rule with a relatively small number of quadrature points turns out to be sufficient. Intuitively, this is because the wave functions are assembled from B-splines, which are of relatively low order. We have also studied the finite element convergence for valences up to 8, as shown here. What we have found is that the convergence rates are still optimal using the SB-splines, but somehow with a higher valence, the convergence constant increases as shown in all these convergence plots here. To summarize, we have proposed a conceptually simple constructions on unstructured quad and hex meshes. So the construction uses the partition of unity method to blend 2 sets of basis functions, and the result is a set of globally C1 continuous basis functions. We have considered a quadratic case, but this really extends to higher polynomial degrees. And we have seen how using the SB-splines we don't need expansive quadrature. And we have observed optimal convergence rates for the biharmonic problems in 1 dimension and 2 dimensions. Although we did not study the convergence in 3D, we managed to show that the solution, the finite element solution, is globally C1 smooth and it's also accurate in 3D. If you are interested, please have a look at our preprint. For future works, we would like to suggest the extension to non-uniform B-splines because we have only considered uniform B-splines in our work. Also, we suggest to look into more complex configurations of extraordinary edges and vertices. So for example, we have seen the lines and joints, and the question is, what if all this sophisticated configuration comes into close proximity? So that is, they come to very close to each other. So that leads to the third suggestion, which is if we manage to define more complex weight functions, then that means we can deal with more complex configurations, especially for hex meshes. With that, I conclude my talk. And if you have any questions, please feel free to send them to me. I'm happy to answer any questions.